In this question, we have two situations, the first of which is that we have a cart moving with the speed of v0 on a frictionless track, and it collides elastically with another cart that is initially at rest. So we have a v0 equal to 0. Oops, let me erase that. And so afterward, they collide elastically. What we know is the momentum before equals the momentum after. And, what we might expect then is that this is going to go off with the same momentum this has, and that might have a velocity equal to 0. In the second case, same thing happens, but the two stick together and go off together, like so. So how does the speed of the two-cart system's center of mass change at all during the collision in each trial? Well, this is not intuitively obvious, but we've seen this before, at the center of mass, whereas the total momentum of the system remains constant. Well, the system, for us, is these two. And the momentum of the system is the sum of these two momenta, and the center of mass is moving with that velocity. So it is moving at some speed slower than v0 because it's all the mass. But in any case, the center of mass at this instant in time is right here. But as they get closer, as v gets closer, the center of mass moves and stays between them until it is them when they collide. But that center of mass continues moving as if these two particles didn't exist. Imagine we take these two carts, we combine them into one to make them so small you can't see them, but they have the same mass. And so that little compressed object is moving along. Whatever happens to those carts before, during, or after is irrelevant because that system, the momentum of that system, is the sum of their two momenta. So what's conserved is the momentum of the center of mass. So it will continue moving irrespective of what type of collision is, because the momentum of the system is a certain number, and it's the same in both instances. So whether they stick together or one bounces off the other, the center of mass is still going to move at the same amount because this mass is the same, and the momentum is mv. If the momentum stays the same and the mass of the system stays the same, the velocity stays the same. So in trial 1, the center of mass, it doesn't change. They're trying to trick us with trial 2 in the second case because the velocity, we actually, when it sticks together, we know the velocity of the two objects will be less than it'll be less than the velocity of the first object, but it's not less than the momentum of the entire system. So decreases. It just does not change across the board. It's the center of mass that remains constant.